Hi, this is Professor Merrill Lichty. In this video, we're going to talk about the concepts involved with hypothesis testing. And this is actually the second inference process. We talked about estimation and confidence intervals last week. And the idea here is that we're going to make conclusions about statements regarding unknown parameters, such as the population mean or the population proportion and so forth. And those statements are going to be based on the sample data. We're going to start by specifying the null hypothesis, which we call H0, and then an alternative hypothesis, which we call H1. And we assume that H0 is true and place the burden of proof on the sample data to convince us to reject H0 in favor of H1. This is very similar to what is done in the legal system in the United States. The null hypothesis says that a defendant is not guilty, and the alternative says that the defendant is guilty. And then data is collected, evidence is collected and presented to the jury, and the jury has to decide which is the case, either H0, they're not guilty, or H1, they are guilty. Let's look at another example that's not quite as meaningful or impactful in somebody's life, and that is testing whether a coin is fair. So the null hypothesis we would have is that the coin is fair. That's business as usual, and I don't have any real reason to believe it's not fair. So we'll say that's the null hypothesis. And the alternative hypothesis says then that the coin is not fair, or the probability of success is 0.5. Sorry, it's not 0.5. So pi is the probability of obtaining a heads on any toss, and the null hypothesis is that that value of pi is 50%. So the experiment we're going to do is to flip this coin 12 times and count the number of heads that we obtain. And x, which is what we're going to call that number, is going to be used as a test statistic. And so in order to evaluate whether we're going to reject H0 or not, we have to know how x is going to behave if H0 is true. In other words, we want to know what is the sampling distribution of x. And it turns out in this case to be a binomial random variable with n equals 12 and pi equals 0.5. And we know all about the binomial random variable, and we can calculate the probabilities associated with every value that x can take on, and here they are listed out for us to see. We can also look at it in a graphical form, and you see it's symmetric and it's nice and pretty. And this is everything we need to know about the random variable x, which is the number of. We can see from this graph that 6 is the most likely event, or the most likely number of heads, and then 5 and 7 is the next most likely, and 4 and 8, and so forth. And as we get out to the tails, we see that those values are much less likely than the ones in the middle. So we can look at this plot or the table and see that the probability of getting 0 heads or 11 or 12 heads is very small, and that's what we mean by when we say evidence in favor of the alternative hypothesis, is probabilities that are very small if the null hypothesis were true. And so we need to come up with some sort of decision rule that tells us when we're going to reject the null hypothesis based on the data that we observe, or in other words, the value of x that we observe. And so looking at the table or the graph on the previous slide, we will say we're going to reject the null hypothesis if x is either 0, 1, 2, 10, 11, or 12. So we now have a decision rule or a procedure for this hypothesis test, and this is just like any other procedure in that it is subject to error. And what types of errors do we have in hypothesis testing? Well, first of all, type 1 error is when the null hypothesis is true, but the test conclusion is to reject the null hypothesis. In other words, H0 is true, but we conclude that it's not true, and so we reject it. And we're going to call the probability of that happening alpha. So the probability of a type 1 error is called alpha, and it's also called the level of significance for the test. The other type of error that we can have is when the alternative is true, but we don't reject the null hypothesis. And we're going to call that beta. So beta is the probability of a type 2 error. Now, we don't like to have either of those errors happen, and so when we design our tests, we want to do it in a way that minimizes the probability of a type 1 and a type 2 error. However, the focus is generally put on a type 1 error. So to minimize alpha is something that you'll see done quite often, with not as much attention being paid to beta. So let's think about these errors in terms of our jury trial setup. If we have the null hypothesis that someone is not guilty, then a type 1 error happens when somebody who's not guilty is convicted, and that's a mistake. Innocent people are sent to prison, and that's an error. We make a type 2 error when we fail to convict a person who is guilty. So somebody's broken the law, and the evidence just isn't strong enough to convince the jury, but and so they're set free, and that's again something that we don't want to have happen. So let's go back to our coin tossing example. A type 1 error means that we declare a fair coin to be unfair, and so the probability of a type 1 error is just the probability of rejecting H0 when H0 is true. And so what that means is getting either a 0, 1, 2, 10, 11, or 12 when the coin is in fact fair. And if we look at the plot, we can see that that happens only in these tail areas. And if we add up all those values, we see that the probability of making a type 1 error in this situation is about 4%, or 3.84%. And that's not a very high probability, so we're going to be okay with that. Now let's talk about a type 2 error. Beta is the probability that we fail to reject H0 when H1 is true. And in other words, we're going to not reject H0 when pi is not equal to 0.5, when the truth is that pi is not 0.5. Well, we can't actually solve that, because if it's not 0.5, we don't really know what it is. So without more information about what the true value of pi is, we can't really do anything to calculate beta. So what often happens is that we use hypothetical values for pi and calculate the rejection, or the probability of rejection, H0 under that new scenario. And so let's look at the next slide, where we're going to assume that the actual value is 0.7. So the probability of getting a heads on any of the coin flips is 0.7. And we now want to calculate the probability of a type 2 error. So in other words, probability, or beta, which is the probability of not rejecting H0 when H1 is true. So that means we want to know the probability that X is 3, 4, 5, 6, 7, 8, or 9 when pi is equal to 0.7. And this is just another binomial random variable, and this is what it looks like. And the non-rejection area or region is shown here. So if we add up all those probabilities, we find out that beta is about 75%, or 0.7469. So if you think about that, it means that there's a 75% chance that an unfair coin is not found to be unfair. And that is quite a high probability. So we're not too happy with that. Let's summarize what we know so far about this test. First of all, when H0 is true, or if we have a fair coin, we're going to make a type 1 error about 4% of the time. Or in other words, alpha, probability of a type 1 error, is about is 0.0384, or about 4%. This is also called the level of significance of the test. We also know that when H1 is true, and in particular when pi is equal to 0.7, or there's a 70% chance of getting a heads with the coin, the test is going to make a type 2 error 75% of the time, or 0.7469. And so we can think about the probability of making the correct decision when the alternative hypothesis is true by subtracting beta from 1 to get what's called the power of the test. In other words, 25% of the time, if pi is equal to 0.7, then the correct decision will be made, which is not a very high probability. So what can we do about that? Well, if we don't like the power or alpha or any of the probabilities of making the different types of errors, one thing we can do is increase the sample size, and we'll look at a slide or two on that in the very near future. Another option is to change the rejection region or the rejection criteria. However, if I am going to change the rejection criteria, there are implications that come with that. So keep in mind that we want alpha to be small and we want the power to be large. That means beta is small. Well, look at what happens when we change our rejection region. So the original region was x equals 0, 1, 2, 10, or 11, or 12. And alpha with that region was about 4%. And beta was about 75%, which means the power is at 25%. So if we make the rejection region bigger, as we have in this first line, now we're adding in a couple extra points, that's going to not only change our alpha level, but it's also going to change our beta level. So our alpha goes from about 4% up to 14.5%, and that's not good. But look what happens to beta. Beta drops to 50%, and so the power then is about 50%. If we make our rejection region smaller, as in this bottom line, so we're only going to reject if we have x equals 0, 1, 11, or 12, then the probability of making a type 1 error, alpha, goes down dramatically to 0.0062, and the probability of making a type 2 error goes up. So it goes up to about 91%, which means the power of the test goes down to about 9%. So there's always a trade-off when you're going to do this. Well, all this is done with changing the rejection region. What if we could change the sample size? So instead of having sample size 12, we have now sample size 50. And instead of rejecting for 0, 1, 2, 10, 11, 12, we're going to need to change that. But we'd like to keep our alpha levels consistent as possible. So if we say reject for x less than or equal to 17 or greater than or equal to 33, that actually has an alpha level of about a little over 3%. And the power for this is 78% when pi is equal to 0.7. So you can see as the sample size goes up, then we have a more powerful test where alpha is kept about the same. And in fact, we would say that the type 1 error has actually gone down, but the power has gone up significantly, so that's win-win. Just a quick comment about the procedure. In this example, we specified our rejection region and then calculated alpha. In other words, we said reject if x is 0, 1, 2, 10, or 11, or 12, and then we added up the probabilities associated with that under the null hypothesis. And that's typically backwards. Usually you pick alpha and you say, I want alpha to be some number. 5% is the default, and that will tell you what the rejection region is. So that's what we will do in the future. So let's summarize the process we've learned so far. We start with a null hypothesis H0 and an alternative hypothesis. We initially assume that H0 is true, and then we collect some data and see if the data supports H0 or if it supports H1, which will lead us to reject H0. Rejection of H0 occurs if the test statistic falls in what we call the rejection region, or sometimes called the critical region, and that is made up of values of x that are unlikely to occur if H0 is true, which would point us in the direction of H1 instead. The rejection region is chosen by picking an alpha level, and that tells us how comfortable we are with making a type 1 error. And finally, the test should be checked. Most of the time it's not, but it should be, in order to assure that the test has adequate power. That's it for this video.